Hello everybody, welcome to Organic Chemistry. Today I'll be going over some practice problems. This is going to be Organic Chemistry 1. I'm going to start all the way from the beginning. Which of the following contains an atom with a formal charge of +1? All lone pairs are shown. Alright, let's look at number 1. This nitrogen here, I can see there are 4 bonds sticking out, 4 single bonds. Over here, 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 and here. And nitrogen has 5 valence electrons. So bonds count as 1 and lone pairs count as 2. So if nitrogen has 5 valence electrons and there are 4 bonds, we're going to have a formal charge of +1. So 1 is going to be correct. Number 2, the sulfur here. Sulfur is going to have 6. Same with oxygen. Oxygen also has 6, but sulfur has 6. It has 1 bond over here, lone pair over here, and there are 2 hydrogens attached to it, which kind of looks like this. So originally we have 6. And then we have 3 bonds, and we have 2 lone pairs. That's going to give us 1 as well. So that's going to give us +1. Alright, so number 2 is correct, which is D. But let's check 3 as well. So carbon over here has 4 valence electrons. We have a lone pair here, and then we have a triple bond over here. And triple bonds counts as 3, so a single bond counts as 1, a double bond counts as 2, and a triple bond counts as 3. So 4 minus 3 minus that 2 lone pair, it's going to give us -1. So that shows that this carbon atom has a formal charge of -1, which is incorrect. Alright, so the answer is D. Choose the incorrect statement concerning the cation shown. Alright, let's go over every single choice we got. Letter A. Destruction contains a secondary bromide. That's true. This bromine is connected to a carbon over here that's connected to other carbons. So it's going to be secondary. So A is not the answer. This cation is considered a delocalized cation. So the cation they're talking about is going to be this one. It's going to be delocalized because we can do resonance structures. We can push this lone pair onto this bond, and we can push this double bond, 2 of the pi electrons over here, and then we can create something that looks like this. I'm just going to call this our group because I'm too lazy to draw everything out. But like this. The double bond comes here, right? This pair of lone pairs goes over here. Before we do anything, let's check the formal charges. So oxygen has 6. We have 1, 2, 3, 4, 5, right? And then the 6th one from the hydrogen. So this has no formal charges. And then for nitrogen, nitrogen has 5 valence electrons, so 2 bonds from the hydrogen and 2 from the double bond. That gives us 4, and 5 minus 4 is +1. So this nitrogen atom will have a +1 formal charge, and this shows that this cation is delocalized. It changed position. Okay, C. The geometry about the nitrogen atom is pyramidal. When you're doing these type of problems, always draw out the resonance structure like I did over here, and pick the one that has like the quote-unquote lower hybridized orbital. So what I mean by that is, let's look at what the hybridization of the oxygen and nitrogen is. Actually just the nitrogen, because this is only talking about the nitrogen. The nitrogen over here has 3 bonds and a lone pair, so it looks something like this with a lone pair. So this is going to be sp3, like the actual geometry. It looks like a little pyramid. If we look over here on our resonance structures, this nitrogen over here has a double bond and 2 single bonds. This means that's going to be a trigonoplanar, and it's going to be sp2. So is C correct? No, it's not. It's not pyramidal, it's going to be trigonoplanar, because we're looking at the one with the lowest hybridized orbital. C is incorrect. Oh. But let's just go over every single one. Bond X is longer than bond Y. That is true because this bond over here is connected by 2 carbons that are sp3 hybridized. So sp3 hybridized carbons have bonds that are longer compared to sp2 hybridized carbons. So right, this carbon is sp3 because of the 2 hydrogen atoms. This carbon is also sp3. This carbon is sp2. So X is going to be longer than Y. So this is incorrect. You can also think of sp2 as in like it tugs a little bit more. So it's going to be a little bit shorter. E, the compound contains more than one bond dipole. That is correct, because if we look over here and we look over here and we look over here, well, there's going to be some kind of partial positive or partial negative on all these sides. So yeah, there's going to be more than one dipole in this structure. And finally F, there's a cyclohexane ring. Yep, that's correct. It's over here. That's a cyclohexane ring. So the answer is C. Select the order that has the following acid correctly arranged with respect to increasing acidity. So which one is most acidic and which one is the least acidic? Before we start this question, I want to show you this. Do a mnemonic. It's called Cario. C stands for charge. Whenever you see a negative or positive charge anywhere on the molecule, it shows you whether it's going to be very acidic or very basic. And these are ordered in importance. So if you see like a positive charge, and then you can immediately assume that's like pretty acidic. So C stands for charge. A stands for atom. The 3 main atoms we're going to be looking at is sulfur, oxygen, and nitrogen. And sulfur is going to be stronger than oxygen, which is stronger than nitrogen. So if you ever see a sulfur compared to an oxygen or compared to a nitrogen, the one with the sulfur is probably going to be the stronger acid. R stands for resonance. If there are more resonance structures, it's going to be more acidic. I stands for induction. Induction means that kind of like on the side of the molecule, there's going to be usually a halogen atom. And whenever there's a halogen atom, it kind of tugs from the, I guess, the main group, which makes it more acidic. And there's an example on this question, so I'll get to that later. And finally, O means orbital. So sp is going to be more acidic than sp2, which is going to be more acidic than sp3. First, let's go look at charge. All right, I don't see any negative or positives. So let's look at atom. Immediately, I see these 2 have oxygen atoms, and this has nitrogen. And nitrogen is going to be weaker than oxygen. So I know 1 is going to be the weakest acid out of all of them. That means I can cross out these. Look at resonance. There's nothing I can do with resonance. I mean, I could move the lone pair over here, but so can every single other atom or molecule. So we can't do anything with resonance. But for induction, number 2 has a fluorine atom, and this fluorine atom basically kind of pulls the electron towards itself and making this a little bit more positive. So this makes 2 the most acidic, and this makes 3 right in the middle. So B is going to be the answer. Select the correct statement concerning the Newman projection shown below of 2,3-dimethylpentane and its other staggered conformations. And look, there's so much, but it looks like it's asking either this is the most or least stable. And so let's see. We have a methyl-methyl interaction, another methyl-methyl interaction, and a methyl-ethyl interaction. So we have 2 methyl-methyl, and we have 1 methyl-ethyl. And let's draw the 2 other ones, 2 other possible conformations. I'm gonna spin the back one, why not? So this used to be a methyl over here, I'm gonna spin it to here. There used to be a methyl over here, I'm gonna spin it to here, and then there's a hydrogen over here. So let's see. We got 1 methyl-ethyl, 1 methyl-methyl, 1 methyl-ethyl, and another 1 methyl-ethyl. So we have 1 Me, Me, and 2 Me, Et. So already we know that this conformation is going to be less stable than the one that's given to us. Alright, and finally, let's check the last one. So there used to be a methyl over here. Let's spin it the other way now. Let's go over here. There used to be a hydrogen here. Let's spin it the other way. And then the last one's a methyl. And I'm going to copy everything over. Alright. 1 methyl-methyl. 1 methyl-ethyl. 1 Me, Me, and 1 Me, Et. So this one over here is going to be our most stable conformation because it has the least interactions with each other, and this one's going to be our most. So let's go through all the answer choices. It says A, this is the most stable staggered. No, it's not. This is wrong as well. This is the least. It's not the least either. It's right in the middle. So it's either E or F. Let's look at E. This is neither the least stable nor the most stable staggered conformation. The most stable staggered conformation contains 1 methyl-methyl, right? And 1 methyl-ethyl. Alright, so it looks like E is correct. But let's look at F. This is neither the least stable nor the most stable staggered conformation. The most stable staggered conformation contains 2 methyl-methyl Gaussian interactions. That's incorrect. There's only 1. And a methyl-ethyl. So E is going to be the correct answer for this question. For our final question, what type of orbital are the 2 lone pairs on oxygen considered to be residing in the following cation? This oxygen has kind of like 4 things, I guess, 2 bonds and 2 lone pairs, making this sp3 hybridized. We also have to look over here. There's a plus over here. There's a cation over here. And this means that the lone pairs, or the lone pair over here, might go over here. So what I'm saying is it could potentially form some kind of double bond where the plus charge is on the oxygen instead. So that's a possible resonance structure that could happen, right? And remember, when we are looking at any type of orbitals, always look at the lowest hybridized orbital. So in this case, this is sp3, but in this resonance structure, this is sp2. sp3 is incorrect. So I'll just remove every single one that says sp3. And you can see that only 1 pair of electrons moved. So if it moved, that means it's in the pi system and it's in the p orbital. So at least one of them is in the p orbital. The other one did not move and stays on the oxygen, and we already know the oxygen is sp2, so the electrons over there is going to be sp2. One is in the p orbital, it's in the pi system, and the other one is sp2, so the answer is B. Alright, that's it for now. Thank you for watching, and hopefully I will see you in the next one.